When sizing an electrical service for HVAC equipment, it's crucial to adhere to the National Electrical Code, or NEC. The NEC mandates a 100% demand factor for HVAC, indicating that the electrical service must accommodate the full connected load of all HVAC units. To accurately size the service, one must first determine the total connected load. This involves calculating the amperage requirements for each piece of HVAC equipment, including compressors and heating elements. In this specific scenario, there are 3 5-ton heat pumps, each with a 60 amp circuit for the compressor and 2 60 amp circuits for the heating elements. Additionally, there is one 4-ton heat pump with a 40 amp circuit for the compressor and one 30 amp and one 60 amp circuit for its heating elements. Calculating the total connected load for the 3 5-ton heat pumps involves adding the compressor amperage and the heating element amperage for each unit. Each 5-ton unit requires 60 amps for the compressor plus 60 amps times 2 for the heating elements. This results in 60 amps plus 120 amps, which equals 180 amps per 5-ton heat pump. Because there are 3 such units, the total amperage for the 5-ton heat pumps is 180 amps times 3, totaling 540 amps. Next, calculating the total connected load for the 4-ton heat pump involves adding the amperage of the compressor and all heating elements. The 4-ton unit requires 40 amps for the compressor plus 30 amps plus 60 amps for the heating elements. This results in a total of 130 amps for the 4-ton heat pump. To determine the overall connected load, add the total amperage of the 5-ton heat pumps to the total amperage of the 4-ton heat pump. This is 540 amps plus 130 amps, which equals 670 amps. Given this calculated connected load of 670 amps, a single 400 amp panel is insufficient to handle the HVAC equipment's electrical demands. Consequently, there are several options to consider. Firstly, one option is to split the circuits between 2 panels. This involves installing 2 separate 400 amp panels and strategically dividing the circuits to ensure that neither panel is overloaded. For example, one panel could be dedicated to the 3 5-ton heat pumps while the other panel handles the 4-ton heat pump. This approach distributes the load more evenly and reduces the risk of overcurrent. Secondly, one may consider installing a larger panel. Instead of using 2 400 amp panels, a single panel with a higher ampacity rating, such as a 600 amp or 800 amp panel, could be installed to accommodate the entire connected load. This option consolidates the electrical distribution into one central location but may require more extensive modifications to the existing electrical infrastructure. When dividing the circuits between 2 400 amp panels, a balanced distribution strategy should be employed. The goal is to ensure that each panel's load is approximately equal to prevent one panel from being excessively burdened. This can be achieved by carefully assigning circuits to each panel based on their amperage requirements. The 3 5-ton heat pumps, with their substantial amperage draw, could be connected to one panel, while the 4-ton heat pump and other ancillary electrical loads are connected to the other panel. Alternatively, circuits can be split based on location or function within the building. For example, one panel could serve the HVAC equipment in the gym, while the other panel serves the HVAC equipment in the classrooms. This approach simplifies troubleshooting and maintenance by isolating electrical systems based on their physical location. When installing a larger panel, it is essential to consider the panel's physical size, mounting location, and accessibility. The panel must be large enough to accommodate all the necessary circuit breakers and wiring connections while also being easily accessible for maintenance and repairs. Additionally, the panel's mounting location should comply with all applicable building codes and regulations. It should be installed in a dry, well-ventilated area that is free from obstructions. Furthermore, when selecting circuit breakers for the HVAC equipment, it is crucial to choose breakers with the appropriate ampacity rating. The circuit breakers should be sized to protect the wiring and equipment from overcurrent conditions such as short circuits and overloads. The breaker's ampacity rating should be equal to or slightly higher than the amperage rating of the circuit it protects, but should not exceed the wire's ampacity. In addition to the main service disconnect, each HVAC unit should have its own dedicated disconnect switch located within sight of the unit. This allows for easy isolation of the equipment during maintenance and repairs. The disconnect switch should be rated for the voltage and amperage of the HVAC unit it serves. Furthermore, the wiring used to connect the HVAC equipment to the electrical service must be properly sized and installed. The wire gauge should be appropriate for the amperage of the circuit it carries to prevent overheating and voltage drop. All wiring connections should be made securely and in accordance with the NEC. It is also essential to ground the HVAC equipment properly. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The grounding system should comply with all applicable codes and regulations. Moreover, when working with electrical equipment, it is crucial to follow all safety precautions. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves, and energizing circuits before working on them. If unsure about any aspect of the electrical installation, consult a qualified electrician. It is generally recommended to split the circuits between two panels to avoid overloading any single panel. In this case, install two 400 amp panels and divide the circuits as suggested above. Firstly, verify the voltage. Ensure that all HVAC equipment is compatible with the voltage of the electrical service. HVAC units are typically designed to operate at either 208 volts, 240 volts, or 480 volts. The electrical service must provide the correct voltage to ensure proper operation of the equipment. Secondly, calculate the total load. Accurately calculate the total connected load of all HVAC equipment, including compressors, heating elements, and any other electrical components. This calculation should take into account the amperage and voltage requirements of each piece of equipment. Thirdly, select the appropriate panel size. Based on the calculated total load, select an electrical panel with an ampacity rating that is sufficient to handle the entire load. The panel should have enough available breaker slots to accommodate all the necessary circuits. Fourthly, install overcurrent protection. Install circuit breakers or fuses to protect the wiring and equipment from overcurrent conditions. The overcurrent protection devices should be sized appropriately for the circuits they protect. Fifthly, use proper wiring methods. Use appropriate wiring methods for the installation, including selecting the correct wire gauge, conduit type, and fittings. All wiring should be installed in accordance with the NEC and local codes. Sixthly, provide adequate grounding. Ensure that the HVAC equipment is properly grounded to protect against electrical shock. The grounding system should comply with all applicable codes and regulations. Seventhly, install disconnect switches. Install disconnect switches for each HVAC unit to allow for easy isolation of the equipment during maintenance and repairs. The disconnect switches should be located within sight of the units. Eighthly, label all circuits. Clearly label all circuits in the electrical panel to identify the equipment they serve. This will make it easier to troubleshoot and maintain the system in the future. Ninthly, inspect the installation. Before energizing the system, thoroughly inspect the installation to ensure that everything is properly connected and installed. Correct any deficiencies before energizing the system. Tenthly, test the system. After energizing the system, test each HVAC unit to ensure that it is operating properly. Verify that the voltage and current are within the specified ranges. By following these steps, you can ensure that the electrical service for the HVAC equipment is properly sized and installed. The selection of appropriately sized conductors is also a key element in the design of an HVAC electrical system. The National Electrical Code, specifically Article 310.15, covers the requirements for conductor ampacity. The ampacity of a conductor is the maximum current in amperes that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Several factors influence the ampacity of a conductor, including its size, insulation type, ambient temperature, and the number of conductors bundled together. Larger conductors have a higher ampacity than smaller conductors because they have a greater cross-sectional area for carrying current. The insulation type of a conductor also affects its ampacity. Different insulation materials have different temperature ratings, which affect how much current the conductor can carry before overheating. Common insulation types include THHN, THWN, and XHHW, each with different temperature ratings and applications. Ambient temperature is the temperature of the surrounding environment in which the conductor is installed. As ambient temperature increases, the ampacity of a conductor decreases because the conductor is less able to dissipate heat. The NEC provides tables that list the ampacity of conductors at various ambient temperatures. The number of conductors bundled together in a raceway or cable also affects their ampacity. When multiple conductors are bundled together, they generate more heat, which reduces their ability to dissipate heat. The NEC requires that the ampacity of conductors be derated when more than 3 current-carrying conductors are bundled together in a raceway or cable. The derating factors are specified in NEC Table 310.15 Kern. To determine the appropriate conductor size for an HVAC circuit, one must first calculate the load current. The load current is the amount of current that the HVAC equipment is expected to draw under normal operating conditions. The load current can be calculated using the following formula: I equals P/volts XPF, where I is the load current in amperes, P is the power in watts, volts is the voltage of the circuit, and PF is the power factor. Once the load current has been calculated, the appropriate conductor size can be selected from the NEC tables. The conductor must have an ampacity that is equal to or greater than the load current, taking into account any derating factors for ambient temperature or the number of conductors bundled together. In addition to selecting the appropriate conductor size, it is also important to select the correct overcurrent protection device for the circuit. The overcurrent protection device, such as a circuit breaker or fuse, is designed to protect the wiring and equipment from overcurrent conditions, such as short circuits and overloads. The overcurrent protection device should be sized to protect the conductor, but it should not be larger than the ampacity of the conductor. The NEC provides guidance on selecting the appropriate overcurrent protection device for different types of circuits. Moreover, grounding and bonding are essential for the safe operation of HVAC equipment. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Bonding ensures that all metallic parts of the electrical system are electrically connected, which helps to equalize voltage and prevent electrical shock hazards. The NEC requires that all HVAC equipment be properly grounded and bonded. The grounding system should consist of a grounding electrode conductor, a grounding electrode, and a grounding busbar. The grounding electrode conductor connects the grounding busbar to the grounding electrode. The grounding electrode is a metal rod, pipe, or plate that is buried in the ground and provides a connection to the earth. The grounding busbar is a metal bar that is used to connect all the grounding conductors together. Bonding is accomplished by connecting all metallic parts of the electrical system together with bonding jumpers. Bonding jumpers are typically made of copper wire or metal straps. The NEC specifies the minimum size of bonding jumpers for different types of equipment. Also, surge protection is an important consideration for HVAC systems, especially in areas that are prone to lightning strikes or power surges. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage transients caused by lightning strikes or power surges. SPD work by diverting excess voltage to ground, which prevents it from damaging sensitive electronic components. The NEC recommends that SPD be installed at the service entrance and at all critical equipment, such as HVAC units. SPD are available in a variety of types and sizes, so it is important to select the appropriate SPD for the application. SPD are typically rated by their surge current capacity, which is the maximum amount of current that the SPD can divert to ground. Finally, regular maintenance and inspection are essential for ensuring the safe and reliable operation of HVAC electrical systems. Regular maintenance should include inspecting wiring, connections, and overcurrent protection devices. Any damaged or worn components should be replaced immediately. Inspection should be performed by qualified electricians who are familiar with the NEC and local codes. The electrician should inspect the entire electrical system, including the service entrance, panels, wiring, and equipment. Any deficiencies should be corrected promptly. In addition to regular maintenance and inspection, it is also important to keep accurate records of all electrical work performed in the HVAC system. These records should include the date of the work, the type of work performed, and the name of the electrician who performed the work. These records can be helpful for troubleshooting problems and planning future maintenance.